Welcome to the first video on Introduction to Linear Programming. This will be our kind of prototype example of Geppetto's workshop. We'll return to this example several times throughout the course. I like it because it's a nice small problem. It's a 2D problem, so we'll be able to solve it graphically. And it illustrates a lot of the big ideas of linear programming. So take a moment, pause the video, read the scenario so that you know what's going on. And then we'll go ahead and discuss what makes up a linear program. So I've laid out sort of the key parts of a linear program are the decision variables, the objective function, the constraints. Once you have the constraints, then you can come up with a feasible solution, a feasible region, and our end goal is an optimal solution. So let's break it down and talk about what each of those are. So the decision variables in a optimization problem in general are the quantities that you actually have control over. So they're the decisions that you make as an organization. I often think of them as the levers that you can dial up or dial down and that you have some control over. Okay. Later on, we'll get into cases where we'll sort of introduce extra variables that really we don't control. But for now, think of your decision variables as quantifying what you're choosing. Okay. So looking at this problem and reading through it, we've got Geppetto, and he's got two different types of toys that he's making. He's making soldiers in his workshop, and he's also making trains. And ideally, he wants to make the right mix of soldiers and trains. And so the number of soldiers toys that he makes and the number of train toys that he makes are the decisions that he has to make. And he has to make that every week. And so we're going to set this up so that we can maximize his weekly profit. But let's start off with those decision variables. We're going to have two decision variables here. S, we're going to let be the number of soldier toys made in a week. And T is going to similarly be the number of train toys per week. Okay, the thing to remember about these decision variables are these are what we have control over. We don't have perfect control over them, but we have some control over them. There are limits. We can't make as many soldiers or as many trains as we want. There are some limits. But these are the things that we have control over. Next part of the formulation is the objective function. This is what we want to maximize or minimize. So either we can set up the problem as trying to maximize something that we like profit, or oftentimes we'll set up a problem so that we're minimizing something that we want to avoid, such as cost. So we might want to set up a problem that minimizes cost while meeting certain minimums. But in this case, we're going to reading it. We want to maximize Geppetto's weekly profit. So our objective function is something that we want to maximize, and I'll follow the book's sort of nomenclature and use Z for my objective function. Doesn't have to be, but I guess I could write it out as what it actually is. But in this case, this Z is going to be the weekly profit. And now we need to come up with, well, what is the weekly profit in terms of the number of soldiers and trains that Geppetto makes, right? So it's not going to be independent of those, but we need to know how many soldiers and trains, and so we'll use our variables as stand-ins for the number of soldiers and the number of trains. So that profit per week will be something times the number of soldiers plus something times the number of trains. Okay, and for a linear program, we need a linear combination of these, and so we'll always have a constant here times soldiers plus a constant here times trains. So what is this constant? Well, if we look at the scenario, each soldier uses sells for $27, but uses $10 worth of raw material, and also we've got a overhead labor cost of $14 as well. And so the net profit per soldier is going to be the 27 minus the material cost of 10 minus the overhead cost of 14. And that will leave us with a net profit of $3 per soldier multiplied by the number of soldiers per week. And that will give us the profit per week from soldiers is 3 times S. Similarly, for the number of for trains, we can look at the profit per week generated by trains. And in this case, a train sells for $21, but it uses $9 worth of material and has an overhead cost of $10. And so 21 minus 9 minus 10, and we'll get a profit per train of $2 net profit. And that's $2 per train, multiplying that by trains per week, and that will give us the profit generated by making those trains each week. Okay, and so yeah, our objective is what we call a linear combination of our decision variables, means that we got a constant times our first decision variable plus a constant times our second decision variable. Okay, next we want to come up and talk about the constraints. So these are our decision variables. These are what we have control over, but we don't have unlimited control. We can't make as many as we want. There are some reasonable constraints on the number of each that we can make. So reading through the scenario lays out a couple of constraints. So we have limits on labor. We've got 2 types of labor. We've got carpentry and finishing, and a soldier requires some of each, and a train requires some of each. And so let's maybe write out our constraints in words, and we'll and then we'll fill in what the formulas are. So we're going to have a limit on carpentry. We're going to have a limit on finishing labor. And then if we read the problem, there's demand for trains is unlimited, but there's a limited demand for soldiers. So even if we made more soldiers, at most 40 soldiers are going to be sold. And so we'll have another one here, which is demand for soldiers. And then we're going to have another, well, I'll save the last set of constraints for just a bit. So let's talk about each of these. So carpentry labor, we have a total of 80 carpentry hours. And so the carpentry hours used has to be less than or equal to 80. So that's sort of our upper limit, but what uses up carpentry? Well, each soldier, let's see, soldier requires 1 hour of carpentry. So 1 hour per soldier times the number of soldiers will give us the carpentry hours used up by the soldiers. And so that's sort of hour per soldier. And if we multiply that by the number of soldiers, that will give us the carpentry hours used up by soldiers. Similarly, we can think about the carpentry hours used up by trains. And for trains, let's see, a train requires 1 hour of finishing, 1 hour of carpentry. And so we also have 1 hour per train times the number of trains. And that will give us the total hours needed for carpentry. So it's 1 times however many soldiers plus 1 times however many trains. The important thing to note is for a linear program, the left side of our constraint is going to be a linear combination of our variables, meaning that we got a constant times a variable plus a constant times a variable, and continuing on. We can have more constants and variables, but in this case, we got 2 decision variables. Similarly, we need to think about what are our finishing labor requirements. We have a total of 100 finishing hours of labor available. Each soldier requires 2 hours of finishing. So 2 hours per soldier times the number of soldiers. And then for trains, each train requires 1 hour of finishing. And so we've got a requirement of 1 hour per train times the number of trains per week. The left-hand side of this constraint will give us our total finishing requirements per week. Okay. And that has to be less than 100 because we've only got 100 hours of that finishing labor available to Geppetto. Demand for soldiers is a little bit easier. At most 40 soldiers are body each week. And so we don't want to make any more than 40 soldiers. And so soldiers per week should be less than or equal to 40. The last constraint type is one that is usually part of a problem because usually our decision variables are positive quantities or at least non-negative. And so our last set of constraints, and these are often implicitly assumed in most linear programs, is that you've got non-negativity constraints, which means that our number of soldiers per week should be greater than or equal to 0, and number of trains per week should be greater than or equal to 0. We can't sell anti-soldiers or anti-trains and somehow recoup labor from them. So we're not allowed to have negative soldiers or trains. And this is pretty typical of most linear programs, is that whatever you're deciding, usually your decision variables are some sort of activity, and you can often only have positive amounts of that activity or none of that activity. It's a little bit rarer to see scenarios where you're allowed to have negative amounts of a certain activity. They do come up, and you can kind of maybe come up with some thoughts in your head about what might be a scenario where it makes sense to have a negative variable. And we'll talk about how to deal with those later on. So our feasible region, we want to think of the feasible region as the region in our variable space. So if we think of the spaces of soldiers and trains and all the possible combinations of those, the feasible region is the region that satisfies all constraints. The nice thing with a linear program and one with just 2 decision variables is we can nicely draw a picture of the feasible region. So I'm going to go ahead and draw a set of axes here. I'll draw these pretty small, but I'll label the horizontal axis as S, the vertical axis as T. Okay. Later on in just a second, I'll show you how to use technology to draw these graphs. If you're not great at drawing graphs, don't worry. I'll show you how to graph some of these using technology in just a bit. So maybe let's start off with the easiest ones, which are the non-negativity constraints. You'll notice I'm really only worried about the first quadrant here where both S and T are positive. I'm not interested in over here. And so it might be worthwhile to say, okay, T is greater than 0, anything that's above the s-axis, and similarly, I need to be to the right of the t-axis. Okay, so that's all good there. Now let's go ahead and go one by one through our constraints. So let's talk about carpentry. We've got 1 times s plus 1 times t equals 80. Oftentimes, the easiest way for me to graph these is to essentially plug in numbers for s and t and figure out where they end up on this graph in this plot. And so the easiest values to plug in are plug in 0 for one and then 0 for the other. And so if I plug in 0 for t, and then solve for what value of s makes this an equality. The trick for graphing inequalities is graph them as equalities and then decide which side of the line you want to be on. And so if I plug in t equals 0, then s has to be 80. And so here's a value of 80. And then if I plug in s equals 0, then t would have to be 80 to make this equality. And so I'll plot that there as 80, and then I'll draw a nice straight line between the two there. Now the trick is, which side of that line do I want to be on? And my usual method is choose a point not on the line as a test point. And usually the easiest point to use is use the origin, as long as that's not on the line. So 0, 0, if I try to plug that in 0 for s and 0 for t, I get 0 on the left-hand side, and 0 is less than or equal to 80, so that's good. So I do want to have the side of the line that includes the origin here. And so I want to be going, I'll kind of draw these out off to the side and draw some arrows pointing down in this way. Okay, so I want to be above the axis, and I want to be on this side of these lines here. Okay, so that was my carpentry constraint. Now let's do our finishing constraint. If I plug in t equals 0, then 2s equals 100. So s equals 50. That ends up being right about there. And then if I plug in s equals 0, then 1t equals 100, or t equals 100. And so that's going to be right up there. And so then we're going to get this line through here, and I'll sort of extend it a little bit beyond. And if I plug in 0, 0 for s and t, I'll get a true statement. And so I want to shade towards the origin here. And so I'll draw my arrows on this one, pointing this way. Okay. Next up, we'll do our demand for soldiers. And so that's going to be right here at 40. S equals 40. And this is going to be a vertical line. S equals 40. And so we're going to draw that just up like this. And we want less than or equal to 40. And so we'll shade this way. Okay. In the end, we need to figure out what is the region that satisfies all the constraints. And so I'll shade that in pink. And that's going to be everything that's on the correct side of all those lines. Okay, so that pink region there satisfies carpentry, finishing, demand for soldiers, as well as the non-negativity constraints. Okay. Last step is to figure out what is the optimal solution. And here's the big idea. The big idea of linear programming is that optimal solutions occur at corner points. Okay, let's reason a little bit about why that might be. So let's return to our objective. 3s times 2t. We can actually think of the vector 3, 2 in the st direction, and maybe I'll sketch that vector on this graph here, and that would be 3 units in the s direction, 2 units up, and so it's going to be going this way. That's the direction. that will increase our objective. As long as we move in that direction, we will increase our objective value. And so if I'm in the middle of the region, in the interior of the region, I can keep moving in the direction of that arrow and I will get better and better solutions. Okay. Once I hit an edge, then it's maybe a little bit harder to keep moving. But as long as I move on the edge in a direction that's at least not perpendicular to that line, I can still improve. Okay. And eventually I'll end up at a corner. And at a corner, it's potential that there's neither direction along either of those constraints will improve it. Okay, and we'll dive into that a little bit more later. But for now, you can just maybe take it as a statement of faith, is that optimal solutions occur at corner points. So then to solve this graphically, we need to find out what the corner points are. And so let's take a little bit of a detour and let's jump into Desmos, because yes, wouldn't be a bad idea to be able to solve this by hand for all these intersections, but it's a little tedious. And so let's use technology both to recreate this graph. I'll be honest, I'll do some graphs by hand in this class, but it's not my strongest suit. And so feel free to use technology to augment your graphing abilities. My favorite sort of graphing utility is Desmos. And so I'm going to go ahead and switch over to Desmos. Okay, let me minimize that. Okay, so here we are in Desmos. It's a nice utility as a graphing calculator. And I can go ahead and type in my constraints here to construct my feasible region. Okay. Now, Desmos doesn't like it when we use variables S and T, but would prefer that we use X for the horizontal axis and Y for the vertical axis. So let's do that. So my first constraint was 1S plus 1T is less than or equal to 80. That's going to translate into X plus Y is less than or equal to 80. And to get less than or equal to, you can just type a less than followed by an equal to, and it will automatically update. Now, it looks like that shaded everything. So I'll go ahead and need to zoom out a ways so I can see it. But here I go. I see that it intersects the x-axis at 80 and the y-axis at 80 as well. So that is my carpentry constraint. Let's do my finishing constraint, which is 2 times my s variable, which I'm now calling x, plus 1 times y, and that has to be less than or equal to 100. And so I want the region where both of these are satisfied, as well as being in the first quadrant here. And then I also have my third constraint, which is demand for soldiers, and that's the s variable, which is we're calling x, and we want that to be less than or equal to 40. Okay. I could add the non-negativity constraints, but it gets a little bit busy. I do, though, have the axes here, which help out, and will play the role of the kind of boundaries for the non-negativity constraints. So here are my 3 what are called functional constraints. The non-negativity constraints are often sort of treated separately. Okay, recreated my feasible region. Now, the nice thing is a tool like Desmos will tell you where the intersection points are. And so I'm going to jot these intersection points down. First off, we'll also note the origin where my 2 non-negativity constraints is also a corner point. So I'll start with 0, 0, 40, 0, 40, 20. This one over here, 2060 is a corner point on my feasible region, and then 080 is another corner point. So I'll go ahead and jot those down and move back to the .cam. Okay, I've jotted down my corner points here. I've also made a column to record the objective values at each of those corner points. Now, because I know that my optimal solution will occur at a corner point, I only need to check 5 corner points rather than every value in the whole region. Okay, so it drastically cuts down on the number of points that I need to check. And so now I can go back to my objective function, which was to maximize that profit per week. And I can use the function 3 times the S value plus 2 times the Z value and compute that for each of my corner points. And so for the 0, 0 corner point, that would be correspond to making no soldiers, no trains, and I'll get no profit. So pretty boring solution, but it's good to know that we at least have one solution that won't lose us money. Now, if I make 40 soldiers and 0 trains, then I'll do 40 times 3, which is the profit per soldier, plus 2 times 0, and that will give me a profit of 120. Now, if I make 40 soldiers and 20 trains, I'll still get the 120 is the profit from the soldiers, and I'll get an additional 40 units of profit from the trains. And so that will give a profit of 160. At this corner point, there's 20 times 3 or 60 as our profit from the soldiers, and 2 times 60 or 120 as the profit from the trains. Adding those together, that gives a total profit of 180. Our last corner point, we make no soldiers and all trains. And if we make all trains, we'll get 2 times 80 or 160 as the total profit there. Okay, so I've got 5 corner points. Here are the objective values for each of those corner points. And now it comes to just selecting the best. The best in this case is the maximum, because our objective is profit and we want to maximize profit. And so this here is going to be the optimal solution. Okay, so this was a start to finish prototype example explaining the different parts of a linear program, as well as how to set up the feasible region. I encourage you to use Desmos whenever it's a 2D problem to solve it graphically. The big idea on where to find the optimal solution is that they always occur at corner points. And so then we just need to check the objective value at each of the corner points, and the best one will be the optimal solution.